All right. Sorry, trying to get the audio on and off there. Took a minute. Let me get my example up in the book. So we're going to continue our talk on hypothesis testing. Bill, I have a large quantity of videos I've been recording for you that I'm going to be posting once I make sure, I have my sound on, since I did 3 of them without the sound on. I had to go back and redo. Hopefully everyone can hear me now. I've got sound on this side and I'm looking good on the other side there. All right. So we're going to be looking at hypothesis testing, but we're going to do this when we don't know what the standard deviation is for the population, which means that we're back to t-tables. I told you those t-tables would come back, and so we're going to use students t-table on this. So that's where we're going to approach this, is the students t-table. So here we do our hypothesis testing on a single sample, and we'll go from there. And so we have an unknown population standard deviation. And this, I think, is more like what you see in reality. You tend to have your measured sample values, and you're trying to figure out what the population is doing. So students' t-tables are very useful. Again, our key is the t-table and calculating the p-values using a t-table for the critical values instead of a z-table. None of the techniques or the questions change. So I'm going to go really quick over the hypothesis and the choosing which tailed test to do. Because remember, we're going to look at the alternative hypothesis for that. We're going to choose the direction the inequality points. So if your alternative hypothesis is a less than sign, you have a left tail. If your alternative hypothesis is a greater than, you have a right tail, because that's the way those signs point. And if you have an inequality for your alternative hypothesis, it's a two-tailed, because the inequality sits in the middle of them. And so we end up finding critical values using a t-test. So everything we did in the previous section carries over. We identify our level of significance. Now, because we're using a t-table, we have this new thing called degrees of freedom, which is the number of samples minus 1. It's the amount of freedom we have in determining what our statistics are, is because we have to have one value to be the sample, and then we compare the samples back to each other. And so our degrees of freedom is the number of samples minus 1. We use the critical values for the t-table, which are in the appendix of the book, and we pull those together here. Let me make sure I have those. I'll open up my Pearson here. 2 seconds. Did you hear me type in the background? I think that has become probably one of the defining sounds of the electronic meeting age, is people typing away in the background of things. All right. See if 143 opens. Good. Make sure my browser's showing on here. Yep, that's looking good. So there's the e-text. If this opens it up in another window, I'll have to change things around, but this should do it. Possibly do it. There we go. And we'll go to our menu, and we want the appendix tables, so the B tables, and we want the standard normal. No, we don't want standard normal. We want the student's t-table. Sorry, t-distribution. So I'll put that there. And I do like this particular version of the graph on this. Let me clean out my, not graph tables. I'm trying to get this, there we go. Because it shows where confidence intervals are, and it shows the tailed test. And it has predefined columns for your different alpha values or your level of significance that you're setting. And so it has a one tail and a two tail column that we need to look for. And so when we use this for the level of confidence, we use the top row, figuring out what our level of confidence was. Now when we do our tailed tests, we use these next columns, depending on it. And notice a two-tailed test is the complement of a level of confidence. And that is why these two ideas are related. I kind of like this table because it also shows the tail graph on it, which I find helpful. All right, let's get back here. And so that's the resource we're going to be using when we try to figure out our hypothesis testing, is we're going to be looking up these values in these tables. And so our values will stick near the table values coming across. And so we use the values for the left and right tailed with the one tail column, and the two tail, we take the one with the two tails. Our setup is going to be very similar, right? We find the value of the test and we look at our 1/2 value as the area within there. And so, for example, if we want to find a critical value for a left-tailed test, given that our level of significance is 5 and our number of samples is 21, well, we find our degrees of freedom, which is 21 minus 1. That gives us 20. And we go over, and let's look at this table now. And let's see how this table works for us with these particular critical values. So let me go over here. There you guys are. And then we'll come over here. Make sure, yeah, all right, good. I'm in the right place here. And so we have a one-tailed test, a left-tailed test with a significance of 0.5. So one tail, 0.5, no, 0.05, sorry, slightly decimalistically dyslexic there, 0.05, and our degrees of freedom was 20. So we come right down here, and there we have 1.725 will be our critical value. Now, if it's a left tail, it's going to be negative 1.725. And if it's a right tail, it's going to be positive 1.725. So that is how these tables turn into the critical values that we're looking at. And in this case, it was a left tail, so we get the negative sign on it. So we have a 5% level of significance. We have 21 samples. That means our degree of freedom is 20, and we come across. So our ability to find critical values are the same. So when we ask our questions, we're going to be taking t-scores instead of z-scores. All right, so doing the same thing, we have a right-tailed test with a level of significance of 1% or 0.01, and we have 17 samples. So our degrees of freedom is 17 minus 1, or 16. So we're going to come back to our table here. And so we have a one-tailed test with a 0.01 and a 16 degrees of freedom. So we come down until we get to 16 degrees of freedom. And that's 2.583. It's a right-tailed test, so it's a positive 2.583. Make sure everything got back to where it is. All right, so we come down here, and we have a critical value of 2.583. Am I on the right one? Yeah, all right. Still worried about this switching back and forth. All right. And last but not least, we're going to look at a two-tailed test. So we're going to have a negative and a positive critical value, right? And our rejection regions will be outside of that, what's in between those, right? We're defining rejection regions, as we did in the last section with these. And so we look at the level of significance we need and our number of samples. Now, because we don't know the population standard deviation, we're using a t-table. We talk in degrees of freedom, which is the number of samples minus 1, or 25 degrees of freedom. So let's come back. There you guys are here. So I'm at a two-tailed test, right, with a 0.10 level of significance. So I'm going to be looking at a two-tailed test, a 0.10 level of significance, or alpha value. And I had 26 samples, which makes me have 25 degrees of freedom. So 0.10 here, down to 25 degrees of freedom here. And so my critical value is 1.708. Being that it's two-tailed, it will be a negative 1.708 for the left end boundary and a positive 1.708 for the right end boundary. Let's get back here. Make sure you're going to hear me talk about every time I switch the presentation view. This is for every now and again it wasn't switching off the web browser for me, and I think I found out why, but I'll keep double checking it. And so that's how we find critical values for t-values. We have a different table that we look at. It is the t-table, the student's t-table, and we use this when we don't know anything about the population. This is probably the most common thing, right? We don't have anything we can say about the population, so we use t-values. And so what we end up doing for the t-values that mimics what we did for the z-values is we calculate t-scores. We calculate this t-score, which relates the sample average to the population average over the sample standard deviation divided by the square root of n. And so the conditions we need to make for this are all similar to what we've been using in the other test. We want random samples, and we either know that the population is normally distributed or we have more than 30 samples. Again, knowing things are normally distributed, if the process is random, if the process is working around a set of natural laws, usually a normal distribution is not a bad idea of our distribution. But if for some reason there are modalities to it, then you need to increase your samples. I as a person, really like talking that if you do anything, just make sure you have more than 30 samples. But that's not always possible. And so we want to do this. So everything is exactly the same as we did for z-score, except we do not know the population standard deviation. We've lost a bit of knowledge, so we're going to have to use a t-table. So our verification process is the same. We want to verify that we don't know the population standard deviation, and we're going to state our two hypotheses, our null hypothesis and our alternative hypothesis, right? Our null hypothesis has the equal sign in it. Our alternative doesn't. Our claim can be either. We're going to specify the level of significance we want to look for. And then on top of that, we're going to identify our degrees of freedom, and we're going to determine our critical values. We're going to compare our critical values with a t-score, And then we're going to make our rejection test, right? We're going to see if that p-value that comes out of it is less than or equal to alpha or greater than alpha, right? And we use that to make our rejection claims. So let's do some of these. This, again, the aggravating part of statistics is we do very, very similar things. We use slightly different formulae based on the conditions. And so the condition we have here is, for lack of a better phrase, we don't know jack shit about the population, right? The population is completely unknown. And we have some samples we have done. And we want to infer about the population with these samples to a level of confidence, right? And this is probably the more realistic way of getting to our statistics. So we want to use that. So let me see if I can do one here. Let's use a rejection region. And I'm going to do a two-tailed test. So this is example 5 in the textbook. Get over here. There's my pen. Scroll this. So example 5. See if I'm writing right. Example 5, yep. And let me see if I can find example 5 in the text here for us. Industrial. There we go. I'll put the problem up here first. So, and I'm going to read through this and look for some things that we need to know. So an industrial company claims that the mean pH level of the water in a nearby river is 6.8. Now pH is a scale that measures acidity and base nature of a solution. pH of 7 is pure neutral. As your pH goes up, I think your base nature goes up. I always forget that. I higher your pH because it's an inverse log. I think high pHs are high pHs are base and low pHs are acidic. And so 6.8 is saying this is slightly acidic water, is what this is claiming. And we want to select 39 water samples and measure the pH of each. It's actually not a hard thing to measure the pH. The more acidic the water is, the more electroconductive it can get. And so a simple amp meter can be turned into a pH meter as long as you set up controls on it. So this is a doable experiment. If we were at the Mount, I would have been so inclined to maybe even run some samples like this to show it. This is always the point in statistics where doing some things is always nice. And so we take all these samples. Our sample average is 6.7, and the standard deviation of our samples is 0.35. And so what we want to do is we're either going to reject the company's claim. And so we're going to make the company's claim. Well, the company's claim is that the pH is 6.8. It's an equality claim. So that's going to be the null hypothesis. So let me come over here and put this up on our blackboard. Switched over to the blackboard. All right, so the null hypothesis is that the pH of the water is 6.8. It's a quality claim, and that's the claim. As I write my M's weird. Not the clam, but the claim. So this is our claim. Now, so our alternative hypothesis is the complement of this. And so that's that the population average is not 6.8. All right, that's not too bad. And what was our level of significance? Reading that back, it said we want a level of significance of 0.05. So alpha is equal to 0.05. We ran the experiment and our X bar was 6.7. And our standard deviation, and notice I'm using an S because it's the sample standard deviation, was 0.35. All right. So I'm just going to switch back here and we'll look at this again. They claimed 6.8. We took 39 samples. We got a average of our samples of 6.7, a standard deviation of 0.35, and an alpha of 0.05. And so the only thing I didn't put in here was that our number of samples was 39. All right, so we've converted all those words into our mathematical symbols, and we're ready to make our decisions and do our calculations. First off, I've got an alternative claim that has an inequality sign in it. And it's the equal sign. So this is going to be a two-tailed test. And those are going to be my rejection regions. All right, so we don't want to fall in the rejection regions. Right, so, and I do draw out my graphs. I know when we get to the table will show the little regions on there, but as I'm putting together what I'm doing, I want to think about it, and this works for me, is labeling everything. All right, so I do not know the population standard deviation, but I have more than 30 samples, so I'm going to use a t-test. So I will want to find my t-values using this formula. And I will want to find the critical values, my t critical and my negative t critical, here and here, because I want to find the critical values for the rejection region. I'm testing the claim, so I'm going to find out, do I fall within the rejection region or not? So these critical values, I'll put TC. I'm going to put, it's going to be plus or minus, because whatever I look up will be plus or minus. So the first thing I want to do is I'm going to look that up on the table. And so I need to know my degrees of freedom, which is one less than my sample. All right, so let's look up the critical value. I need a better mouse pad. They're hearing that click, 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 click. All right, there you guys are. And over to my scale here. So we had a two-tail of 0.05, and we have 38 degrees of freedom. So I want to come down this third column to 38, which is right here. And so my critical regions are going to be 2.024. So I'm going to come back here, go back to the blackboard, and my critical value regions are plus or minus 2.024. And so I do not want to fall in this rejection region coming across, or I will reject the claim, right? All right, so let's calculate where my t actually ends up being. So I'm going to switch colors here so I can put things over top of the yellow. And so my average of my samples was 6.7. I'm going to subtract that from the claimed population average. I had a standard deviation of my samples of 0.35. I want to divide that by the square root of 39. Now, where did I put my calculator? I was fighting with this thing earlier. All right, so parenthesis 6.7 minus 6.8 parenthesis divided by parenthesis 0.35 divided by second square root 39. Close out my parentheses. And I get a negative 1.784285142, or approximately negative 1.784. So that number is right in there. So this is not in the rejection region. So we cannot reject the null hypothesis. We fail to reject the null hypothesis, and so we state this as there is not enough evidence to reject the claim. Or we could say there's enough evidence to support the claim, right? They made a claim, it's within the supporting of the evidence. Either of those would work well. We could also use p-values for a t-test. To get the p-value, you would need to use a calculator or some other device to calculate the value of the integral. We don't have it as exact as a table, but p-values do list what happens. For t-tests though, and actually in all of these tests, me as a human being, I prefer mapping critical values. Because this critical value line, be it a t or a z critical value, will be the same for my level of significance, whatever the claimed value is. And so I can drop those lines down, and then I can find out if my t-score falls within those regions or not. It's a consistent way of doing it, and that's how the book works it out. It does a p-value with the TI-84, but not everyone has a TI-84, so I am not going to ask on you to do the p-values of a t-test. I will on a z-test, but not on a t-test. All right, so that gets us through the two types of tests that we can do on means and how we can find the means for our population, given that we know the standard deviation or we don't. So let's look at the next section. Let me load up the next section here. There's that. Okay, we're still on that. So I'm going to look at section 4, and we're going to be testing proportions. And we're going to be using a z-test for proportion statistics coming across. And that will finish chapter 7 for us. We're not going to look at the variance or the standard deviation. We're just going to look at proportions. Hypothesis testing, I don't know. For me, being able to say, are we able to support claims or not? I've done a lot of experimentation type things where we've had to check it, and the idea of testing your claim versus sorry, I'm trying to switch this one file while I'm doing this. I can't talk and walk. Can't walk and chew gum at the same time. All right, let me here. Sorry, as I switch my slide layout. There we go. So hypothesis testing, I think, is actually one of the better things that we've been able to do with statistics. We're able to take the idea that we've made a claim and we turn it into a mathematical test. And it lets us start putting a level of certainty to how we update what we know. We're updating our level of information. I'm going to have to switch windows here because this does this. Whenever I change slides, there we go. And our ability to know information and update what we know with levels of confidence work out. I actually wish I had an extra 24 hours here, because I was just watching there with the COVID-19. There is a treatment that has in a blind test, showed an 8% mortality rate versus 11% on the placebo. Now they ran 1,000 cases. I would like to look at that percentage using a hypothesis test for proportions. And maybe I'll work that out as a side video to see what the level of significance that is, right? But that's really what we're doing here, is we're having the ability now to, if I can look at something, if I can look at a statistic, and I can say, I can make this claim that this thing is better than this other thing, that we can measure it, and that we can measure it so that we can make decisions based off of it. It's funny, I learned all this as writing experiments and going, this is our level of error, and this is how confident we are of this. It took me a while, I think, outside of the science realm to actually understand that is making a decision. And when I started seeing statistics applied to things external from science and getting the language right, how this is all a decision process. It's how we update our knowledge. And being able to measure that, I think, is useful. And hypothesis testing is the best way we have of doing it. Now, I want to stress, and I will always stress, for any of this or every of this to work, we need to be as random as we can be. Blind, double-blind tests. Just making sure that randomness goes in, that we're not biasing the data, that we don't have some parameter in the background that's actually changing the results, and that we're never 100% sure. All of these level of confidences, level of significance, it's the best based on what we know. And philosophically, I read the Greeks on their different philosophies, and I've become, I kind of fall under the realm of solipsism. You can't actually prove anything. Right? You have to somewhere believe in something, and I believe there's a reality, right? But I can't prove that. Feels real, it feels real. But then outside of that, I update what I know with certain levels of uncertainty, and we add information. And this science, what I've said is, from day one, we were looking at how we could measure it and use the tools of mathematics to improve what we know about reality. But if we're completely honest, philosophically, mathematically, and scientifically, at the end of it all, we can't say anything's real or not. So we can never say anything's 100% sure. And this does this with the numbers. That's why we have levels of confidences and levels of significance. And I know I'm beating on this one thing with the only stick I got. But if you get anything from this course, I really want you to understand that, right? That confidence is measurable, and it's never 100%. All right, so we're going to test population proportions. And one of the things about the population proportions here is, if we remember our Z tests for the confidence level on them, we want the multiplications between the number of things we have and our proportion to be greater than or equal to 5. So that we can use a binomial distribution. And the test is the stuttering Jeff. The test statistics we're looking at is going to be a percentage value, a p-value, but not the same p-value as we were just doing in the hypothesis test. We're looking for a proportion value. That's why it gets the little hat on it. And so what we're able to do here is we're able to make a z-test on the proportion values. We're able to take our test proportion and find our values for it. And these are the things we did in section 6. And so what we want to do is we're going to go through the same thing. We're going to state the claim mathematically. We're going to identify the null and alternative hypothesis. We're going to specify a level of significance, and we're going to determine our critical values using the Z table. Notice this is a Z test again. And we're going to compare the Z test against this new Z score. And so we're making a Z score for a particular population. So let me jump right into an example, because we've done the stating the claim. We just have a different type of test. Again, I'm in the repetition part of statistics here. So this is in section 7.4 in the textbook. It's going to be example 1. And let me switch to example 1 here, which is 1, 2, 2, 2. And I'm skipping over these. These are in the book really nicely on page 388. But it's nothing new. We've been doing this over and over and over again. We have been stating our claim mathematically, making a null hypothesis and an alternative hypothesis, letting the alternative hypothesis determine the tail of the test. And then we take our statistic and we make a test score out of it. And here we're going to make a Z score. So let's look at this and see what is different with it than the mean value. Now, before in the mean value, we were saying the average is blah, and we would list some number, like 6.8 for the pH value. Here, a researcher claims that less than 45% of US adults use passwords that are less secure because complicated ones are too hard to remember. So notice, I'm not saying what the mean or the average is. This is a percentage. That's what these proportion values are percentage values. And so my p-value here is 0.45. Immediately, no matter what type of data I have, I could have multiple amounts of data, but if one proportion is a percentage, I can immediately turn it into a binomial distribution, because the complement, or the other side, is the rest of the choices. All right. And so my Q value here is going to be 0.55. It's the other side of that. And so that's the 55% of adults that passwords aren't less secure, right? This could actually have been a 3 question, right? You could have 45% are less secure, so many percent are secure, and so many percent are more secure, right? This could be a gradated thing, but because we're looking at one bin, and that one bin is the less secure bin, we can look at the less secure bin and everything else, the 0.45 and the 0.55. So we take a random sample of 100 adults, and 41% say they use passwords that are less secure because complicated ones are too hard to remember. At a significance level of 0.01, is there enough evidence to support the researcher's claim? All right, let's go over here to a blackboard and put all of these values together. So get over here. I'm on the blackboard. It has switched over, and it is very black. What color I'm going to use sky blue or cyan, I think it's calling it here. So first thing is I have a significant level. I always forget to write the significance level. One of the things you find if you do end up doing statistics a lot, you'll probably use 0.05 or 0.10 almost all the time. So when I do these problems, I tend to forget to write down the alpha because I always use the same. And for me, when I'm doing statistics on like research data for MWCC, I always use a 0.05 alpha. And so I'm making sure I write that first there. So our Level of significance is 0.01. All right, so our claim is that less than 45% of the adults. Well, it's less than, right? Not less than or equal to. So our P is less than 45%. And I'll make it 0.45. And so this is our claim. Our claim is going to be the alternative hypothesis here. Right? And a lot of times, more often than not, when we're doing a claim, if we do not say a value is exactly equal to something, we tend to use the less than or greater than inequality. Rarely do we say it's less than or equal to, right? But to make this work, those boundaries are really important. And this is what we've been doing each time. If it has the equal sign, it's our null hypothesis. And so in this case, our null hypothesis is P is greater than or equal to 0.45. Notice, and since I haven't talked about it in one lecture, and I'll talk about it here, the combination of the null hypothesis and the alternative covers every possibility. You're either going to be less than 0.45 or you're going to be greater than or equal. That covers every possible statistical value. That lets us mathematically map these spaces out. That's why we do our alternative claim and claim that way. Well, our test says that N, what is our N here? We surveyed 100 adults. And our experimental proportion was 0.41. Make sure I'm reading back. Yep, 41% say these. So we did 100 adults. All right, so for this to work, N times P has to be greater than 5. Greater than or equal to 5. Yep, this is an equality. So N times P is 100 times 0.41, which is equal to 41, which is definitely greater than or equal to 5. And N times Q has to be greater than or equal to 5. Now Q whoops. I'm going to go back. That's our experimental, but we want the claim. And the claimed P is 0.45, which makes the claimed Q 0.55. My bad. And so N times P, the claimed P, is 0.45 times 100. And 45 is definitely greater than or equal to 5. And then we also do that for Q, which is 0.55 times 100, which is 55, which is greater than or equal to 5. So this test will be valid. I do not think I have assigned a question where the test was not valid. And maybe I should do that in the future, but it's one of the things where occasionally you will be dancing on the boundary of if you can or can't use these things. And it's good to check. What it really is saying is that the smaller your percentage area is that you're testing against, the more samples you need. Right? If we're only looking for a 1%, 1% of 100 would be less than 5. So we would need 500 samples to make this test work. And so it's a way of determining the amount of N that we need. All right, so we want to figure out what type of test it is. So we look at our alternative hypothesis. Whoops, I shouldn't be. That's not an equal sign. We'll look at the alternative hypothesis. Look at this. Look at this. And that points to the left. So this is going to be a left-tailed test. And so we want to see what our rejection region is, and if we lie inside of it or outside of it. So our Z critical value at an alpha of equal to 0.01 on a left-tailed test. Hey, we get to go over to the browser, get to say hi to everyone here, come over to the text, come up here. So 0.01 on a one-tailed test. So one-tailed test, 0.01, and I had 99. All right. Whoops. Is that I'm on the wrong distribution. I need to go back a page. This was a T table. Need to go to a Z table. Tables, appendices, tables, standard normal table. All right, there we go. Standard normal table. Let's see if I can actually scroll this out. And I'm looking for a 0, 1. I'm having a hard time getting this column to go up here. There we go. And next page. Ah. Go back. Not getting the second half of the page here. All right. Well, I'm going to use the book. Let me find the page number on the book because I'm not getting to the AT table. And this was the page that I wrote out for you guys. Where did it go? On a Z rejection level in section 7.2. And it has a small table of values of the critical values. It was off on the left-hand side. Give me 2 seconds here. I know the number. I just want to show you where to get the number from. It's on page 369. And a 0.01 left-tailed has a Z-score of negative 2.33. That's what I was looking for, 269. And I know it's at the bottom of the table in the front material. I would write that 369. It's in the study tip, and it says a left-right tail with an alpha of 0.01. I actually would write that down on the bottom of any notes that you use when doing things, because we come back to that. And so our Z critical value is negative 2.33. Let me see if I can find page 369 in this so I can show you what I mean. It was on section 7.2. 7.2, page 369, 360. Oh, yep, I can do it right here. I swear I'm using every piece of technology. And right here. This table lists of critical values. Yes, good, it's showing. All right, there you guys are, back to the table list. And so we have an alpha of 0.01. I'm doing a left tail because is it a left tail? Let me look at my thing again. Yes, it is a left tail. And so I want a Z critical of negative 2.33. I'm going to go back to my blackboard. And I'm going to write down my Z critical. So my Z critical is negative 2.33. All right, and that defines my rejection region. Notice how everything is really defining a rejection region. Well, now we calculate our Z score, and our calculation for the Z score is our sample statistic minus the claimed population statistic. And then in using the binomial distribution, we get PQ divided by N. Notice this is all under the square root sign. All under the square root sign. Slightly different than what we were having before. All right, so we got a measure of 0.41. The claim was 0.45. And so we want the square root of 0.45 times 0.55 divided by 100. I always found that these proportions and these percentages really beg for calculators. they get really, really catchy numbers. And so negative 0.41, so parentheses 0.41 minus 0.45 parentheses square root 0.45 times 0.55 divided by 100. Me and the calculator are fighting. The calculator wins. Let me do that again. Second square root. There we go. And I get negative 0.80403, that goes on. And so we'll say negative 0.80. Well, that is not in the rejection region. So there is not enough evidence at 1% to support the claim. Remember, the claim is the alternative hypothesis. The rejection region rejects the null hypothesis. And so I failed to reject the null hypothesis. So I have failed to reject the null. So we have to say that the evidence is not enough to change the null hypothesis. Well, the claim was the alternative. So we're saying there's not enough evidence to support the claim. All right. That is hypothesis testing. This is how we update information based off of using statistics to measure how much error our sample measurements can have, and using levels of significance. All four sections, section 7, 1, 2, 3, and 4, use the same idea. You create these rejection regions. Right, being if it's a two-tail or one-tail. And you can find the critical values on either side of that, or you can find the p-value. And if your result does not fall in the rejection region, you can't reject the null hypothesis. If your result falls into the rejection region, you reject the null hypothesis. That will tell you about your claim, depending on if your claim is your null or your alternative. And so for all of these, we have this similar idea. We're measuring our claims and the amount of errors that will come out with our claim, right? Because the null hypothesis and the alternative, when we reject the null and that level of significance, is talking about the number of type 2 errors we get. And so what we're trying to do is, by setting a level of significance, we're trying to minimize the amount of error we can get. All right, that's everything I have for you guys today. We will start chapter 9 on Monday, and we will finish comfortably by the last day of classes on May 11th. We're only doing sections 1 and 2 for chapter 9. All the work is up on Pearson right now. If you have any questions, holler. I have a pile of videos to record for 2-3 of you coming from questions out of Pearson. I have started recording them. Like 2 of them, the sound didn't work on them, so I've got to re-upload those. But that's what I'm doing tonight. So I'll be out on the porch watching the neighbors drive by and recording replies to your questions from Pearson. Everyone be safe, be well, and I will talk to you shortly. Have fun.